All right, so the plan for today is just to finish up a last couple of problems in section 5.5. I actually originally had slated one problem for lecture and two problems for the worksheet. I think I'm going to cut that down to one for the worksheet just for time considerations, because we also have two sections to get through today. Starting the chapter on polynomials, chapter 6. We'll be talking about adding and subtracting polynomials and some kind of a starter on multiplying polynomials. So we'll also be talking about what polynomials are. So just kind of a heads up, chapter 6 is where things start to kind of ramp up a little bit more in difficulty. So in chapter 6 and future chapters, we're going to see things like factoring and rational expressions, and all of that builds directly on the algebra of polynomials that we'll be learning starting here at the beginning of chapter 6. So this is material that, in order to understand that those more complex concepts later on, you want to have a really firm foundation here. So when you go through 6.1 and 6.2, drill these problems, do practice problems from the book, do extra practice problems that you make up or from Khan Academy or something. Make sure that you're really firm in these foundations from the beginning of chapter 6, so that when we get to the more challenging material, like say factoring or like say rational expressions, this stuff, this more foundational stuff would be just second nature at that point. And the quote of the day today is from Marcus Aurelius, the Roman emperor who Roman emperor / kind of philosopher, I suppose. He wrote a book that we these days title Meditations, and so he was probably in the line of like Stoic philosophers. I would say I'm no expert in philosophy, but Stoicism is kind of making the rounds again, and it's in vogue these days. So you might see people with this on their whatever Instagram post or photo or whatever. Just this quote, "Be one" by Marcus Aurelius, and that comes from a line in Meditations that maybe can be roughly translated. He was a Roman emperor. He wrote in Greek, so maybe roughly translated from the Greek is something like, "Stop arguing about what it means to be a good man, be one." So kind of in other words, I think there's maybe two ways to think about this. Is one, don't spend so much time kind of pointing yourself in the right direction you never take a step forward. We've already talked about this a little bit with things like studying and academics and so on, that you can over plan. You can spend so much of your time and effort planning on how you're going to say study for an exam that you never quite get around to studying for the exam. Now, that doesn't mean that you just go and do random stuff with no planning, but there should be a balance there. I think another interpretation might be something like it's often a lot easier to do that planning process in a sense, maybe not with studying, maybe it's about as easy to do one as the other, I don't know. But it's a lot easier to sit in, a nice, cool, air-conditioned, den or something with all of your buddies and sit there talking about, oh, what does it mean to be a good man? Should we do this or should you do that? That's a lot easier than actually going out and actually into the world and doing the good thing most of the time. So anyway, that's the quote of the day today from Marcus Aurelius. All right, let's come down then to this problem, wrapping up chapter 5. And remember, we're in chapter 5, we're dealing with systems of equations, systems of linear equations, and particularly this is a mixture application. So we have that a 40% antifreeze solution is to be mixed with a 70% antifreeze solution to get 240 liters of a 62% solution. How many liters of the 40% and how many liters of the 70% solutions will be used? So let's say that the number of liters of the 40% solution and of the 70% will be Y. And on one hand, I know I need to get a total of 240 liters, so I know that x plus y has to equal 240. And on the other hand, I know what percentage antifreeze I need. I should pretty quickly just do a reasonability check. I want to get a 62% solution by mixing 40 and 70% solutions. 62 is between 40 and 70, so this seems like a reasonable thing that I could accomplish. So if I mix x liters of a 40% solution, I have 0.4x. So 40% antifreeze solution, let's say that means 40% antifreeze and 60% water. So 0.4x would be the amount of antifreeze in x liters of solution. And then 0.7y would be the amount of antifreeze in y liters of solution. And I want this to equal the total amount of antifreeze that I want to have in the full 240 liter solution. So I want a 62% solution, 0.62, times the number of total liters that I have, 240. Oh, that looks like a 9, 240. So this is my system of two equations in two variables. And coming over to the calculator, let me switch my share here so that you can see my calculator. Oops, I was messing around in another class with this, so I need to make one change to a setting really quick. There we go. Okay. So coming over to our calculator, going to the y equals menu, I suppose I'll choose to solve these for y in terms of x. Y equals 240 minus x, that's not bad. This one down here, you might take a couple of steps to solve this for y in terms of x, but here we'll get y equals, we get 0.62 times 240 minus 0.4x. That's what we would get when we isolate the variable term, and then isolating the variable, divide by 0.7. So I wrote this in a notation here that's maybe a little more calculator-esque. Instead of kind of the fraction being numerator over denominator, I use the slash line here. And that just kind of helps me think through where do I want parentheses and so on when I type this in the calculator. Okay, so my first equation, 240 minus x. And my second equation is what I have here, y equals parentheses 0.62 times 240 minus 0.4 times x, and the parentheses divide by 0.7. So that looks good. Let me go to my window. And here I know that x and y both should be between 0 and 240, right? Because I want a total of 240 liters. So let me just start with 0 to 240 on each axis. So for x min, x max, as well as y min, y max, going from 0 to 240. And I should get an intersection on my graph. Okay, I see an intersection on the top left. So I have a bit fewer liters of the x solution and a bit more of the y solution, it seems. I could start trying to zero in on that and get a better idea where I think that intersection is. But with 240 units kind of in play, that might take some time. I'm going to use the calculate menu. I'm going to do second trace. and 5 for intersect, or I could navigate down and search for an intersection. The first line I want is y equals 240 minus x. That's good. I'll hit enter. The second line I want, that looks right. I'll hit enter. The guess, it doesn't really matter. I'll just hit enter again. And I see an intersection at x equals 64 and y equals 176. So I need 64 liters of the 40% solution. And 176 liters of the 70%. That'll give me a total of 240 liters of a solution that's 62% antifreeze. Now, this would be a problem that is much nicer to solve on the calculator than to even do something like substitution. The substitution wouldn't be too bad here. We could pretty easily solve, say, this one for y and plug in, or we could just equate these two sides. But then I have all of these decimals and things floating around. It's not a very nice problem to solve, right? The kind of by hand algebraic way of doing it is going to be pretty cumbersome here. We could do it that way if we wanted to. Again, that was just a tangential note because that material is not technically covered till 108. But even if I was good at the addition elimination method or the substitution method, I probably would still prefer the graphing method in this case because it just would be a hassle to deal with all these decimals. Okay, so let's jump over to the worksheet over here. And since we just did one that's very, very similar to this one, let's pick a slightly different one. And we'll work through this problem. So I'll switch my share back. So this is a little bigger on your screen. Okay, so take a look at this problem. Maybe take about, let's say about 5 minutes or so to work through it. And then we'll come back and we'll discuss it. Okay, so let's take a look at this problem. So we see that $65,800 is the total of the sum of the two loans, the federal loan, which I'll say has amount F, and the private bank loan, which I'll say has amount P. So I note that F plus P has to be 65,800. One of the nice things about coming to community college is that you should end up with nowhere near this amount of student loans. So little plug for community college, I guess. The difficult one is the interest here. So this $2,753.53 represents 1 year's worth of interest. It's the total amount of interest combined between the two loan types. We know the rates of the two loans, 4.5% and 2%. So how do we convert those rates, those interest rates, into amounts, into amount of interest? We multiply by the amounts of the loans. So the amount of interest that I pay on the federal loans is 0.045, 4.5% a year interest rate, times F, the amount of my federal loan. And likewise, the amount from private is 0.02 times P. I add those together to get my total interest paid for the year, 2753.50. And so here I have two equations, but they're in F and P, so I'll pick one of these to call X and one Y. I'll call F the federal loans X and P the private loan amount Y. I just picked them that way. You could have chosen them the other way. Not a big deal which way you choose them. Solving the first equation for quote Y for P, Y is 65,800 minus X. And then solving the second equation, this might take a couple of steps, but we get 2753.50. If we isolate the variable term, we have to subtract off of 0.045x. And then that's all divided by isolating the variable, dividing by its coefficient 0.02. So I did this a little bit quickly. If you want to throw in a couple extra steps, definitely, definitely feel free to do so. And then if we jump over to the calculator, so I go to my Y equals menu, and we see a pretty similar setup to what we had before. 65,800 minus X for Y1. And then for Y2, I have 2753.5 minus 0.045 times X. I need a parentheses there, and then I need to divide by 0.02. So let me just double check that. That looks good. Now my window, remember F and P are the amount of loans for federal and private. I know the total is in the ballpark of $60,000. So let me just, I don't know, I'll just go 0 to 60,000 on both axes. I mean, I suppose I could have gone to 65,000 or 70,000 or something, but we'll see if we get the intersection here. It was just easy for me to type in. Okay, so I do get the intersection. It's all the way at the right of the screen, but it is on the screen. If it was a little bit off the screen, I would maybe just adjust my window. I can do second calc for calculate, go down to option 5, find the intersection. The first curve, 65,800 minus X, that looks good, hit enter. The second curve, this long, complicated one, hit enter there, and then just hit enter for the guess. Doesn't really matter what we pick for our guess. And we find a solution. So our solution, our intersection is at X equals 57,500 and Y equals 8,300. And if we wanted to write out the answer, we might say something like, what's her name? Josie, yeah. Josie has $57,500. What was X? X corresponded to the federal loans. So Josie has 57,500 in federal loans and 8,300 in private loans. So I think the crux of this problem was getting the second equation set up, and in particular, trying to find a way to convert the interest rate information that we're directly given into a form that can be equated to the amount information that it's related to. So 0.045 and 0.02 are interest rates, and 2753.50 is an amount. How do we make those two mesh? And that was a similar challenge to over here. We have kind of amount information. We might have been tempted, if we were just going through this quickly and not thinking too much, we might have been tempted to just put equals 0.62 because we just see the 0.62 there. But we realized that on the left-hand side, both of those terms represent amounts of antifreeze. They're in units of something like liters. So we need to have that extra factor, that extra piece on the right-hand side to make the units work out right, to make everything correct. Are there any questions on anything about Chapter 5, Systems of Equations? Okay, so then we're going to jump into Chapter 6. We're shifting gears a little bit here. We're starting to move away from the realm of linear equations. So far, we've restricted ourselves to linear equations where the only time that we see a variable is when that variable is to the first power. But now we're saying, what if we have instances where maybe we have, sorry, I'm messing with my Zoom windows here, getting things back together. There we go. What if I have a situation where maybe I have some terms with the variable to a power other than one, maybe a second power or a third power? What if I have maybe an x squared term, something like that? So the first thing to note is that we have some semantics here, some language, some definitions to think about. The kind of general idea that we're discussing is polynomials, but some specific cases of polynomials are a monomial and a binomial. So polynomial, kind of coming from the two roots, poly and nomial, poly meaning many, and nomial meaning something like name or something like that. Strangely, poly is really a Greek root and nomial is related to a Latin root. So, I mean, I didn't invent the term, but so we have kind of like many terms. Bi related to the word two, like bicycle or bipedal. And so monomial is kind of like mono and nomial. Calling it, I guess, a mononomial would be like a tongue twister, so we just call it a monomial. But mono meaning one, meaning single. So monomials have one term, binomials have two terms, and polynomials, if we're discussing monomials and binomials and we say, oh, this is a polynomial, we might mean three or more terms. Or we might mean polynomial to be kind of an umbrella term covering monomials, binomials, and entities with three or more terms. So sometimes polynomial is used more broadly as an umbrella term for monomials, binomials, and more terms. Sometimes it's used a little more specifically. It's a little context dependent, but that detail usually isn't super important. So again, we're talking about how many terms we have. So if I have something like 3x squared plus 2x minus 1, a term is a structure connected to the rest of the expression with a plus or a minus. So I see that I have 3 terms. I could have an example like x plus 2. I have 2 terms. So we call this a binomial. Or I could have something like 7x that's not really connected to anything else with a plus or a minus. It's just one term, a monomial. Now, an important note is that before we count the number of terms, we should simplify. We should combine like terms. So for instance, if I had, say, 3x squared minus x squared plus 2x minus x plus 7 minus 2, I wouldn't say that this has like 6 terms. I mean, I suppose in some strict sense it does at this point, but before we determine whether it's a monomial, binomial, polynomial, we should simplify first. We should combine like terms. I recognize that each of these groupings are like terms. How do I recognize like terms? Well, they're things that can be combined together. So these are constants. Constants are like terms with one another. I can simplify 7 minus 2 to 5. Now, when I have a term that has a variable in it, if a term has a variable in it, it's a like term with another term if they have the same variable or variables to the same power or powers. So in other words, 2x minus x, the 2x and the x are like terms because they both have the same variable x to the same power, just the first power. So they are like terms, they can be combined together. This can be simplified. If I have, 2 apples and I take away 1 apple, I have 1 apple left. If I have 2 x's and I take away 1 x, I have 1 left. Instead of writing that as 1x, I'll just write it as x. And then similarly, if I look at the 3x squared and the minus x squared, both of those terms have the same variable, x, to the same power, 2 in both cases. So if I have, 3 oranges and take away 1 orange, I have 2 oranges left over. If I have 3x squared, take away 1x squared, I have 2x squared left over. Now, can I keep combining things? Can I combine the 2x squared with the x? Well, these have the same variable, but it's to different powers. One is to the second power, it's squared. The other is to the first power, it's a linear. Those aren't like terms, they're not going to combine. Could I combine 2x squared with, say, the 5? Well, we don't have the same variables here. The 2x squared has a variable x, the 5 doesn't have any variables in it. These are not like terms either. So if we have different variables or a variable in the lack of a variable, those are not like terms. If we have the same variable, but it's to different powers, those are also not like terms. None of those can be combined together. But at this point, we've combined together We've identified all of our like terms and combined them all together. We've simplified everything in this expression. And now I see three pieces connected together by pluses or minuses. This is three terms. Now we can also discuss the degree of a polynomial. So the degree of a polynomial is the largest exponent that's attached to a variable. I use the word attached here loosely to a variable. So if I was to say, oh, okay, well, if I look up here, 3x squared plus 2x minus 1, I suppose I could write this as like 3x squared plus 2x minus 1 to the 50th power or something. I mean, 1 to the 50th power is just 1. I suppose I could write it that way. It's a bit goofy, but I could. I wouldn't say that this is a 50th degree polynomial because I see a 50 here. That's not attached to a variable. So if I see, a 2 squared or something like that, that exponent doesn't count. What are the exponents that I see attached to the variables? Maybe I'll circle them in red, I guess. I see a second degree here, or a second power here. I see no, I don't want to write an X. I'll write like a frowny face or something. I don't see any exponents attached to the constant. This 2x is a little interesting. But if we have, say, something like x, on one hand, we know that that's, for instance, 1 times x, right? It has kind of this hidden coefficient of 1 that we can either put in or get rid of at our convenience. But similarly, x always carries an exponent of 1 as well. So x also has this kind of hidden exponent, x to the first power. We could even go a little further, and this is maybe pushing a little bit into some future sections, but a constant we can actually think of as having a variable to the power 0. So this might be like 1 times x to the 0 power. Again, this is pushing a little bit into future sections, so if you're not super happy with this idea, not a problem, just hold off for a couple sections. But the important note is that this 2x is really 2x to the first. So we have powers of 2, of 1, and essentially no power, let's say, at this point. So this is a polynomial, 3 terms, of degree 2, or a second degree polynomial. As an aside, we have a special name for second degree polynomials. We call them quadratic polynomials. That's kind of an aside at this point, but we'll definitely be talking about those quite a bit in the near future. So let's look at our next one, x plus 2. The 2, let's just say essentially it doesn't have a power, but x carries the power 1. So this is degree equals 1, or a first degree polynomial we call linear. And we have quite a bit of experience dealing with linear expressions and linear equations, when the only time that we see a variable occurring is to the first power, is when the variable is just by itself. There's not an x squared or y cubed or anything like that. And then likewise, in the next one, 7x, we think of as 7x to the first power. That's a first degree polynomial or first degree monomial, I suppose. And then down here we have a power of 2 attached to the x, a power of 1 attached to the x, then a constant term, which we'll just kind of say has no power for the time being. Or if we wanted to be a little more technical, we could say it has a power of 0. But regardless, we see that the highest power on any of our variables is 2. So this is a second degree polynomial, a quadratic. Okay, so we've introduced several terms. It's probably a good idea to just maybe write these terms all down in one place: monomial, binomial, polynomial, degree of a polynomial, what like terms are, so that you have the definitions kind of at hand. And if you hear a term and you say, wait, I forget what that is, you can just flip back to your little legend and say, oh, okay, yeah, that's what that means. I think that's one of the challenges in a course like algebra is there are often just so many words that we use that are just, not normal words. Like nobody goes around, on Sunday afternoon talking with their buddies about monomials or about ordered pairs or about X and Y intercepts, or right. We have all of these terms that mean very specific things. So it's a little bit like learning a little bit of a new language alongside the logic and the practical aspects of the mathematics. So there's some vocabulary to be learned here, and so having that vocabulary kind of in a place that's easy to get to, where you can quickly look it up, almost like a glossary, might be helpful. Okay, so what if we wanted to start doing some operations on polynomials? Let me zoom this in a little bit so it's a little bigger. What if I want to add and subtract, in this case, 2 monomials? I have a monomial and another monomial I would like to add together. I could write it this way, or it could be written in words as something like add the 2 monomials, 7y cubed and 3y cubed. Well, here, the first thing I look at is, okay, are these like terms? Do they have the same variable? Yes, they do. Do they have the same exponent? Yes, they do. So that means that I can add the coefficients and that'll be the new coefficient of a single term with the same variable to the same exponent, or that's going to be 10y cubed. If I come down to this next problem, I see I have 3 monomials that I want to add or subtract. I want to figure out what is 3x minus x plus 4x squared. I look at these terms and I ask, do any or all of the 3 terms have the same variable? Yeah, they all have the same variable. So they're all still kind of candidates for being like terms. Do they all have the same power? Well, 2 of them have power 1, they're first degree. Remember, if we just see an x, we think of it as an x to the first power. But the other has a second power. The first 2 terms, 3x and x, are like terms, but the third one is not. So 3x minus x would be 2x, just 3 minus 1 is 2, and then append the variable to the power to that, so 2 times x plus 4x squared. And this is the best we can do within kind of a reasonable within reasonable conditions, there's nothing we can do to combine these two together. We can't make these two terms into like a single term. We can't make them, say, a single monomial. We'll see later on that maybe we can do some factoring or something, maybe write it in a different form. But that writing in a different form has pluses or minuses, pluses and minuses. But there's nothing we can do to take the sum of two monomials and simplify it down to a single monomial. At this point, as far as we're concerned for this section, this is fully simplified. This is the simplest form we can get this into. Again, as far as we're concerned for this section. When we are in the factoring section, we might want to do something else to this, but that's for another day. Okay, let's practice these concepts. I don't think this should take a whole lot of time. Oh, somehow I got a plus or minus in there. That's not a good symbol. There we go. So I give you about maybe 2 minutes. Work carefully through both of these. Identify the degree of the polynomial. Identify the like terms. Simplify, and then identify whether it's a monomial, a binomial, or a polynomial. So do those three things: the degree of the polynomial, simplify it, and then is it a monomial, binomial, or a polynomial? So about 2 minutes for this. Shouldn't take very long. Okay, let's take a look at this at these two problems. So the first one up here, we see the highest power attached to a variable is the fourth power. So our degree is 4. This is a fourth degree polynomial. We do see that these are like terms. They have the same variable x to the same power, the fourth power. So I can combine them. I can add the coefficients, and that will be the new coefficient for x to the fourth. So 12 plus 9 is 21. 21x to the fourth is my simplified form. And I note that this is a monomial. This consists of just one term. It's not attached to anything else by a plus or a minus. For our k's down here, we see that our first and third terms are like terms. They have the same variable k to the same power, in this case, the first power. But the middle term is not a like term with either the first or third or anything else. There's nothing else that has a k cubed in it. So the middle term just kind of gets copied down. It just stays as it is. But the first and third terms can be combined together, 5 minus 2k or 3k plus 7k cubed. That's our simplest form. We can't do anything else to get this down to, say, a single monomial. It's kind of fundamentally two terms, and therefore it's a binomial with two terms. Any questions so far? Okay, so let's look at adding two polynomials together. What if I had a polynomial like 5x squared minus 4x plus 3, and I wanted to add that to another polynomial, 3x squared minus 1? So what could I do here? Well, I noticed that I do have parentheses here because I'm adding polynomial plus polynomial, but those parentheses aren't actually super important here, right? If I just get rid of the parentheses, maybe I lose a little bit of the context of where the problem came from, but I haven't really changed the mathematics at all. I could just get rid of the parentheses and nothing changes here. In this example, now that's not always the case. Sometimes the parentheses are super important and we have to be very careful when we get rid of the parentheses. I see that I have some like terms like this 5x squared and 3x squared, this minus 4x. It doesn't seem like it has another term to be combined with. And then I have my constants plus 3 and minus 1. Something that can sometimes be a good idea to do is either to label your terms like this and kind of literally check them off as you take care of them in the next line down, right? There are a lot of terms to deal with here. We could easily miss one or maybe double use one or something like that. Or if we wanted to be really careful, we could put all of our like terms together first. So I have a 5x squared plus 3x squared. Using commutative and associative properties, I can rearrange things and then regroup them how I like. That takes care of my second degree terms. I can actually group those with the parentheses, even if I wanted to be very explicit. My minus 4x, my first degree term. That doesn't have any other first degree terms to combine with it, so I'll just leave it at that. And then my constant terms plus 3 minus 1. I can see that I've checked off all my terms. I've used everything in the next line down. I haven't forgotten anything. And now it's very clear which ones are the like terms, which ones are going to combine together. I have 8x squared minus 4x plus 2. This is a second degree or a quadratic expression. I note that I have three terms. None of these are like terms. None of them can be combined together any further. So this is a polynomial with three terms. And this would be its simplest form. If we look at a similar problem, here we have 6 times a polynomial minus another polynomial. So here we have to be very careful. We have a few things going on. Number one, we now have different variables to different powers. We have m and n. We also have our parentheses that are more meaningful here. I have the 6 multiplied by some stuff. So I need to distribute my 6 through. I get 6 times m cubed plus 6 times n squared minus 6 times 2, 12 mn. So that's what I had to do to get rid of my first parentheses. Right, in the previous problem, I just kind of got rid of the parentheses because they weren't actually doing anything. But here they are doing something. They're showing what the 6 has to be distributed to. So to get rid of my parentheses in this new problem, I need to actually do a good bit of work first. So this all came from this 6 times parentheses. And here I also have to be really careful. It's easy for me to just make a mistake and do minus 2m squared plus 3mn. But remember, this minus sign, in a sense, has to distribute through. Or really, when I think of, if I wanted to be more technical in my language, more technically accurate, when I think of subtracting something, I think of adding -1 times that thing. And then I can very clearly see that this -1 has to be distributed to both. But often we just kind of speak a little roughly and just say distribute the negative. So I have minus 2m squared minus, very important, 3mn. Very easy thing to miss, especially in a longer problem like this where we have a lot going on already. Really easy to miss that last little bit of distributing that minus sign to the 3mn. Now I'm looking for like terms. I'm looking for terms. And my OneNote is freezing up. Let me just restart it here. I can always tell it's about to start really freezing up whenever it won't let me change the pen color. So, but like everything in tech, for some reason, just turning it off and turning it back on seems to solve all problems. Okay, so I'm looking for like terms. I'm looking for the same variable to the same power. I noticed that my 6m cubed has variable m to the third power. Whoops. I notice over here that I have variable m, but to a different power. So I have same variable to a different power. These are not like terms. I think I have enough colors here to indicate all of these. I have a term with just n's, with no m's. I don't see any other terms with just n's and no m's. So this 6n squared doesn't have any fellow like terms. And then if I look at the minus 12mn, the variable or variables present here are m and n. And the powers are first power in each case. So it's m to the first power and n to the first power. And I actually see that these are like terms. I can combine these two together. Everything else, though, the red term, the black term, the blue term, they don't have any other fellow like terms. They just get copied down as is. So I've taken care of these three. They don't have anybody to combine with. They just get copied down. But now I can combine these two like terms. I have minus 12 minus 3 is minus 15 mn. And this is really the best that we can do. It might seem like maybe we would want to simplify more than this, or we'd want to get fewer terms in this, but we can't. This is the simplest that we can make it. We see this as a degree 3 or a cubic. polynomial. So the highest power that we see is a 3. As a side note, we didn't mention this before, but when we have in the same term two different variables with different powers, when we're finding the degree, we add the powers. So we would say that this term is a degree 2 term because it has 1 power of m and 1 power of n. We combine those to make 2 powers. But here, the degree 3, this m cubed, wins out over all of the degree 2 terms. So it's a degree 3, a cubic polynomial, like 3 dimensions, like a cube is a 3-dimensional object. And we see that it has 4 terms. So it's a polynomial with 4 terms. All right, let's work through a couple of these. To take a look at these 2 problems, these are slightly more involved. So let's take maybe about 3 minutes for these 2. So again, work through, simplify them, identify how many terms, whether it's monomial, binomial, or polynomial, and what the degree is. Okay, it's about at 3 minutes. So this one was a little more involved. So if you didn't get all the way through, that's okay. But for this first one, we need to remember to distribute the negative sign, the -1, through to the -3 and make that a +3. I think everything else is pretty straightforward with that simplification. And here I chose to reorder things so that I put my like terms together. And then I simplify. So I get negative 9x squared plus 3x plus 2. This is a second degree polynomial. It's a quadratic with 3 terms. I note that of the 3 terms that are left, none of them have the same variable to the same power. None of them can be combined any further. So this does indeed end up with 3 terms. It's a polynomial. Coming down to my second problem here. This one's a bit more challenging. I have to distribute the 2. So I end up with 2m cubed plus 2n squared minus 6m. And then for my second polynomial that I'm adding on, I can pretty much just get rid of the parentheses. Minus 5m squared minus 2n squared plus m. And here I'm going to go through and look for like terms. Sorry, my allergies are just like going haywire today. So I start with 2m cubed. I'll color that one black. Do I see any other terms with m cubed? I do not. I'll come over to 2n squared. I'll color that one blue. Do I see any other terms with n squared? I do. This minus 2n squared down here, that is a like term. So I'll color that one blue as well. For minus 6m, that's an m to the first power. Do I see any other m to the first power or just m terms? Yeah, the plus m at the end here, I'll color both of those green. Those are like terms. And then my minus 5m squared, that's just the last term that's on here. It doesn't have any fellow like terms. So my 2m cubed, I'll copy down. No other like terms to combine it with. My minus 5m squared, again, I'll just copy that down. No other like terms to combine it with. And where I left off was looking at the n squared terms. I have a plus 2n squared minus 2n squared. I mean, I suppose I could write that as a plus 0n squared, but really that just goes away, right? So these two just cancel out. Plus 2n squared minus 2n squared, that contribution from n squared just goes away, and I'm left with no contribution from n squared. And then I have minus 6m plus m, that's minus 5m. So my bits related to n went away, and I'm left with just these. I see that each of these has a different variable to a different power. So these are not like terms. So I have 3 terms, or a polynomial, and it's of degree 3 because of the cubed up there. All right, any questions on 6.1? I mean, just a second before we move on to 6.2. Okay, so moving on to 6.2. Here we're talking about properties of exponents and how they relate to polynomials and monomials. So we have 3 properties that we're going to be focusing on here. There's the product property, x to the m power times x to the n power equals x to the power m plus n. If we have the same base, If we have the same base, if it's multiplied by another factor with a base to a different exponent, or it could be the same exponent, then we add the exponents. If we have the product of two factors with the same base, then we add exponents. Why is that? Well, let's consider something like x squared times x cubed. We know what x squared means. It means x times x multiplied by, we know what x cubed is, x times x times x. But I also know that multiplication is associative. I can regroup in any way that I want, so I could just get rid of my grouping symbols. If my exponents are integers anyway, this is essentially how the proof would look. We would say, okay, well, x to the m is just m x's multiplied together. X to the n is just n x's multiplied together. And those two products are also multiplied together. I just have m plus n total factors of x that are multiplied together. That is our product property. If you ever get confused with these properties and you think, wait, does it work that way or not? Or, okay, I'm over here. I forget, do I add these exponents or do I multiply them? How does that work? Just take a simple case like this and actually just write it out and see what works. We can see that we end up with x to the 2 plus 3, not, for instance, x to the 2 times 3, like multiplying them together, for instance, if we got a little confused. So we can always just, for a rule like this, just take a simple case and check ourselves if we get a little bit caught up with the details. So the power property, x to the a power all raised to the b power, is x to the a times b. So when we have a power to a power, we multiply the powers. Why is that? Well, what does something cubed mean? It means write the same thing 3 times multiplied by itself. And then what does x squared mean? It means multiply the thing by itself. Then we can get rid of the parentheses and we see this is just x to the 6. So I take what's inside here and I repeat it 3 times, but what's inside here is the variable repeated 2 times. So I have 2 repetitions, 3 times, 2 times 3 is 6. So when I have a variable to a power, and I take that whole thing and raise to a power, I just have the variable to the new power that's the product of the 2 powers. And then what if I have a product of bases, x times y, to a power? Well, here the power just distributes. This is a distributive property. The power just distributes across the multiplication in this way. So in a sense, the power of m distributes into the product and goes on to the x and the y. We get x to the m times y to the m. So when we have a product of bases all raised to a power, then we just raise each base to that power individually. Now, a very important note is notation. If I just have xy to the m, not parentheses xy and parentheses to the power m, this is just x times y to the m. The x does not get the m power here. Where if I have parentheses xy and parentheses to the m, This is x to the m times y to the m. That's just a question of notation of how we communicate the information. If we have parentheses around the xy, then that whole factor xy, or that whole term, I guess, xy, gets raised to the power m. If we do not have parentheses, it's only the factor, the say potential base bit that's nearest the exponent that gets raised to that power. So we just have to be careful with that. This is kind of like the MAT090 idea, like -2 cubed is -8, whereas -2 cubed, geez, brain fart moment, -2 squared. -2 squared is -4, whereas -2 all squared is +4. Yeah, if we do a cube, it doesn't matter. But so this is a similar idea to what we have over here. Okay, so let's look at using these properties to simplify some expressions. I'd like to start by simplifying the product of two monomials. So if I say multiply the monomial 3y squared by the monomial y cubed and simplify, that's what I want to do here. So I have to keep my different situations straight. The idea of like terms is related to adding or subtracting and simplifying additions and subtractions. So I can add and subtract like terms. I cannot add and subtract unlike terms. Now we might get that a little confused because we might come down here and say, oh, wait, these are unlike terms. Does that mean I can't multiply them? Well, no. The idea of like terms and combining like terms is related to addition and subtraction. But we can multiply different factors that would kind of be, in a sense, unlike factors if we wanted to give it that name. That's not a problem. We have, for instance, our product property that tells us how to handle that situation. So we have y squared times y cubed, just to be very explicit about what I'm doing here. This is 3 times y squared times y cubed. And by the associative property of multiplication, I can choose to multiply the y squared against the y cubed and simplify that bit. So y squared times y cubed is going to be y to the power 2 plus 3. Or this simplifies to 3 times y to the 5th. And I won't write the dot there because we typically don't write it when we just have a monomial like this. So I've simplified the product of these two monomials to a single monomial. And it's 3y to the 5th. Again, note that like the 3 doesn't get squared. We don't have a 9y to the 5th or anything like that. It's just the y getting squared. If I add something like 3y in parentheses all getting squared, that would be treated differently. Okay, if I come down here to a problem like this one's a little more complicated. I have a couple things going on here. I have two things being multiplied together, but I also have this kind of power to a power situation. And I also even kind of have a product to a power situation. So where should I start here? I think I would like to start with the product to a power. I think I would like to start with this factor and try to take one step to make things a little bit simpler. In a problem like this, sometimes it can be hard to even get started because there are several operations that we're going to need to do to simplify this. But I note that I can think of this 3 times x cubed all squared. I can see that that is just a product to a power. So I have the product of two bases, 3 and x cubed to the second power. This is going to give me 3 to the second power times x cubed to the second power. Or this is going to give me what? 2 times x squared times 9 times x cubed squared. And I see that the 2 times 9 can combine together to make an 18. So I might as well do that here. And each time that I copy down, I'm being really careful to get all of my factors copied down, not to miss anything. That's a place I could easily make an error. I could forget to copy a factor down. Now I have kind of the 18. There's not much I can do with that. I have a factor of x squared. At this point, there's not a whole lot I can do with that, but x cubed to the second power, I can use a property on that. I have the power to a power rule. When I have a base raised to a power and that whole thing raised to a power, I multiply the two powers. So these first two factors, can't really simplify them any, but x to the third power, all raised to the second power is x to the 3 times 2, or x to the 6th. And now lastly, I see a product property come out. I have the same base to two different exponents multiplied together. 18x squared times x to the 6th is 18x to the power 2 plus 6, or 18x to the 8th. And at this point, this is as simple as I can make it. So I boil this all the way down to 18x to the 8th power. And I had to use 3 different properties to do that. I had to use my product of bases to a power property. I had to use my power to a power property. And I had to use my product property, my sum of exponents property. So let's work through a couple of examples related to these. So take a look at these two problems. Take maybe about 4 minutes or so to work through these. If you haven't already, I'll put this back up for just 20 seconds or so. If you haven't done it already, make sure that you write down these properties so that you can refer to them when you're going through this work on the worksheet. So write down these 3 properties if you have not done so already. Give you about 10 seconds more. Okay, so work through these 2 problems, again, about 4 minutes, and then we'll come back and discuss. Okay, let's talk about these two problems. So the first one I recognize as just 2 times y to the 5th times y to the 7th, or this is just 2 times y to the 5th times y to the 7th, like that. And I note that this is a candidate for the product property where I just add the exponents. The bases are the same, so I just take the same base, y to the power 5 plus 7. That gives me a y to the 12th. And then the factor of 2 just kind of comes along for the ride. It just ends up in the final answer is just the 2. For the next problem, I again see that I have a lot of different things going on here I'm going to have to unravel. The first thing that I kind of notice is that I have a product 2 times x squared to a power to the 5th power. Product to a power property says I distribute the power into the product. So I end up with 2 to the 5th times x squared to the 5th coming from this 2x squared all to the 5th power up here. And the factor of 5x cubed in front just gets copied down. 2 to the 5th is 32. 5x cubed is just 5 times x cubed times 32. And then here I have x squared all to the 5th power. This is a power to a power property. So here I multiply the exponents 2 times 5. So I get x to the 2 times 5. Coming down to the next line, I simplify 5 times 32. Well, that's 5 times 30 is 150 plus 5 times 2 is 10. So 160 times x cubed times x to the 10th. And then lastly, I have the product property x cubed times x to the 10th. Same base, I add the powers, 160 times x to the 3 plus 10, or 160 x to the 13th power. Okay, so how does this work if we have different variables in play? Well, we pretty much just follow the same rules. I look for things that I can combine together using some of these rules. And importantly, I remember that multiplication is commutative and associative. Oh, I missed a factor of 3 there. So I think the first thing I'll do here is kind of start by just writing out all the multiplications, getting rid of as many parentheses as I can. So I have negative 2 times m cubed times 3 times m squared times n. And I noticed that the m's are going to work nicely together, as are the constants. Let me kind of rearrange things a little bit, leaning on the commutative property. So I've got these two factors taken care of. And these two, and that one. I can multiply my constants. Negative 2 times 3 is negative 6. M cubed times m squared, that's the same base. I add the exponents. And my n, I don't have anything to do with that really at the moment. So simplifying, I get negative 6 m to the 5th power times n. Do any of my properties apply here? Can I combine anything else? Can I simplify any further? I don't think so, because m and n are different bases, so I can't combine any powers. And I don't have anything like a power to a power or anything like that, or a product to a power. So this is the simplest I can get this expression, negative 6 m to the 5th power times n. We would say that this is a monomial. We would say it's 6th degree because there are 5 powers on m and 1 power on n, so 5 plus 1, 6th degree monomial. Okay. And coming down to this problem, maybe I'll actually save this one for next time because we've only got a few minutes left. We'll save it as a warm-up for leading into next time. But in our last few minutes, take about a minute and a half or so to do this problem, and then we'll come back and discuss. Okay, so for this problem, again, the first thing that I'll do is kind of split apart all of the multiplications just so I can see very clearly what's being multiplied together. Negative m squared is negative 1 times m squared, and then times 6 times m cubed times n squared. I'll put my constants together out in front. My factors of m, I know that I'm going to be able to do something with, so I'll put those together. And then my little n squared factor, I'll just leave that at the end. Negative 1 times 6 is just negative 6. M squared times m cubed, same base. I add the exponents. That gives me m to the power 2 plus 3. Then times n squared. And simplifying gives me negative 6 m to the 5th n squared. And that's my simplest form. This is a monomial. It's a 7th degree monomial because I have m to the 5th n squared, so 5 powers plus 2 gives me 7 total powers. All right, I'll stop the recording.